Good evening, everyone. Our topic for the presentation is ideal algorithm, random oracle model, vision or principle, birthday problem, attacks on random oracle model. Our team members are myself, Om Prakash Patel, Ravi Teja, Pankaj Kumar, Prabdeep Singh, and Pragya Pandey. Cryptography is the study of secure communication techniques that allow only the sender and intended recipient of a message to view its contents. In this presentation, we are going to discuss some of its techniques, which are ideal algorithm, random oracle model, vision or principle, birthday problem, attacks on random oracle model. Firstly, ideal algorithm. Ideal algorithm stands for International Data Encryption Algorithm. It is an encryption algorithm. It is a symmetric block cipher that takes 64-bit as an input, 128-bit key, and generates 52 subkeys from 128-bit keys to perform 8 identical rounds for encryption, in which 6 different subkeys are used and 4 keys are used for the output transformation. It was intended to replace the data encryption standard. It is also reversible like DES. Following are the steps that are involved in the algorithm. First, 128-bit key divided into 16 bits, which generates 8 keys, in which starting 6 keys used in the first round and the remaining 2 keys are used in the further rounds. For the next round, the original key of 128-bit left shifted circularly by 25 bits and divided into 8 keys of 16 bits each. Now for the second round, we use previous round's remaining 2 keys and the 4 keys for the current 8 keys to till that we can have less than 6 keys. Further, the plain text of 64-bit is divided into 4 blocks, namely P1, P2, P3 and P4, each of size 16-bit, and then along with the sub keys, the 6 sub keys generated from 128-bit keys are transferred into first round. Similarly, for output are generated from the first round are passed into second round, and this process continues till the 8th round. After the 8th round, the output transformation takes the 8th round output and 4 subkeys and generate the cipher text of 64 bits. Here is the following pictorial representation of the algorithm faceless. We can see on the right hand side, the pictorial represents the 128-bit key, which are divided into 6 subkeys. And on the left hand side, we can see there are following 8 rounds along with the output transformation, which uses 6 subkeys to generate the cipher text. Now, in each round, we have 14 steps. Here, the pictorial representation represents the following steps involved in each round. Like in step 1, we multiply the first part P1 and K1, and then we add it, and similarly we go on till 14 step. And in the output transformation, we have 4 steps to generate the cipher key. Now, Pradeep will continue to the next part.
Random oracle model. A random oracle is theoretical black box that responds to every query with a random responsible chosen uniformly from its output domain. Expect that for any specific query, it responds the same way every time it receives the query. That is, a random oracle is a mathematical function mapping every possible query to random response from its output domain. In the random oracle model, one assumes that some hash function is replaced by a publicly accessible random function. This means the adversary cannot compute the result of the hash function by himself. He must query the random oracle. The random oracle model has been used to prove the security of numerous uh, crypto system, and it has to lead simple and efficient design that are widely used in practice. Random oracle methodology. The random oracle model, a popular methodology for designing cryptographic protocols, consists of following two steps. One, first, design an ideal system in which all parties have oracle system to a truly random function and prove the security of this ideal system. Next, one, replace the random oracle with good cryptographic hashing function, providing all parties with a description of this function. Thus, one obtained implementation of the ideal system in a real world where random oracle do not exist. Problem with random oracle. The problem with the random oracle model is that it doesn't really model real life. In real life, there is no random function. there is usually a single fixed hash function that one uses, such as MD5 or SHA1. Therefore, even if adversary may not work for a random function, it may work for the specific one if designed with it in mind. In fact, even if we think that the adversary was fixed before MD5 or SHA1 were designed, we cannot still uh, say that MD5 or SHA1 were chosen at random. A simple counting argument shows this: the number of function in a set of 0 to 1k to the set of 0 of to 1 is 22k. Hence, random function take log base to 22k is equal to 2 power k bits to represent. But this is an exponentially large number of bits, so most function cannot even be represented. The mere fact that MD5 and SHA1 are polynomial time computable makes them special. It is theoretically possible that the adversary would fail for a random function but not for polynomial time one. In fact, Harvey constructed an artificial counterexample, one that probably secure in the random oracle model but insecure when the random oracle is installed in real life with any polynomial time computable function. The status of random oracle model thus is as follows. It allows us to prove a whole lot of practice signature scheme secure, including in addition to full domain hash as well as lot of encryption scheme and other things. But the meaning of this proof in certain as opposed to proof in model without random oracle, which clearly implies that the scheme cannot be broken without violating the security injection. It continues to be used because of its power, but it would be very nice if someone figure out how to prove this thing without random oracle to give us more assurance that these are really secure. I personally view it was the acknowledge our failure. There are a lot of constructions that seem secure on some institute level, but we cannot prove them secure in standard model. So hopefully until we real proof of security, we prove the security in this funny fake model. Next to call Ravi Teja to continue.
I am Ravteja. I worked on the birthday problem topic, and the problem statement is: what is the probability that two persons among n have the same birthday? If we assume that the probability having the same birthday as p same, we can easily evaluate it in terms of p different. So the first person can have any birthday from any of the 365 days, and the second person can also have any birthday excluding the birthday of the first person, and so on. The n person can have any birthday excluding all the previous n minus 1 person's birthday. If we use approximations and Taylor series, then we get the following formula, that is n is equal to square root of 2 into 365 logarithm of 1 by 1 minus p same. If we find out p different, then we can also find out p same.
Now, continuing with the presentation, the next topic is pigeonhole principle. I am Pragya Pandey and I worked on this topic. The pigeonhole principle states that if there are n things are to be placed in m containers where the number of things, which is n, is greater than the number of containers, which is m, then at least one container will contain more than one thing. Please change the slide. Some of the alternate formulations include: if n objects are distributed in n compartments such that each compartment receives one object, then each compartment will contain one object. The other one is: if n objects are distributed over m places and n is less than m, then some compartment will be there which receives no object. Now, some of the examples of pigeonhole principle are sock picking problem, handshaking problem, hair counting problem, birthday problem, as discussed my friend Ravi Teja, subset sum, and team tournament. Now, some of the applications of pigeonhole principle. The first one is pigeonhole sort. This sorting method works well for the lists of element when the number of elements and the number of possible key values are roughly equal. It takes O of n plus range time to complete, when n denoting the number of items in the input array and range denoting the number of potential values in the array. Now, working algorithm of pigeonhole sort. In the array, find the lowest and highest values, be them as min and max as least and maximum values respectively, and max minus min plus 1 will also be a valid range. So create an array called pigeonholes as the same size as the range and keep it empty initially. Now the third step is start iterating in the loop through pigeonhole array in the order, returning elements from non-empty holes to the original array. And now coming to the second application, this principle can be utilized to demonstrate that any lossless compression algorithm, given it makes a few sources of information more modest, as the name of pressure proposes, will likewise make few different sources of information bigger. In any case, the arrangement of all information successions up to the given length L could be planned to the much more modest arrangement of all groupings of length not exactly L without impacts, a chance which categorize standard rejects. The third one is it gives simple evidence that a few things can't be hashed. For instance, assuming that you have 1024 words, you want somewhere around 1024 codes to communicate them. Any other way, two words will guide to a solitary code and you can't differentiate between them. Now, I would like to call Pankaj to continue this presentation.
Attacks on random oracle model. In general, if a protocol is proven secure, attacks to that protocol must either be outside what was proven or break one of the assumptions in the proof. For instance, if the proof relies on the hardness of integer factorization, to break this assumption, one must discover a faster integer factorization algorithm. Instead, to break the random oracle assumption, one must discover some unknown and undesirable property of actual hash function. For good hash functions, where such properties are unbelieved unlikely, the considered protocol can be considered secure. Now, I would like to conclude this presentation. In this presentation, we have majorly discussed about IDEA algorithm and random oracle model. IDEA stands for International Data Encryption Algorithm. It is a symmetric block cipher that takes 64-bit as an input, 128-bit key and generates 52 subkeys from 128-bit keys to perform 8 identical rounds for encryption, in which 6 different subkeys are used and 4 keys are used for output transformation. And random oracle is a theoretical black box that responds to every query with a random response chosen uniformly from the output domain. And further, we have discussed about pigeonhole principle and birthday problem